All right, over to you, Tamas.
Okay, hi everybody. I'm Tamas from ARM. Today I would like to give you about a presentation about attestation and measured boot. The objective is this presentation is to give you a bit more context that what we are doing in the ARM future confidential compute architecture regarding attestation and measured boot. Previously this week we have posted a patch series to the TFA public Gerrit for review, which shows some activity that we are started to enabling these flows between in the software stack. If you have any question, stop me anytime and feel free to interrupt. Okay, so what is attestation and what's its purpose? So in the confidential compute world, you want to ensure that your software stack will run on a certain hardware which provide very strict security properties, and you want your software stack will handle confidential data. So you want to be sure that all the software components running beneath your feet and the hardware is capable to protect these confidential data and provide the security properties what you are requiring. And how to make sure that you are running on a system, because this will be probably in a cloud compute environment and you will just only rent that machine, and you as a software stack owner, realm owner, will be a remote entity. And attestation is a way to build up trust towards a remote system. During attestation, you are requesting a report from a remote system, and in that report, the system collects hardware and firmware properties of the system and cryptographically sign it. And when you receive this report, you can validate, of course, first the signature of the token, and then you can look into the token and you can check, okay, this is the hardware where we are running. These are the firmware components which was loaded on the system. I am expecting this and this and that version from those software components. If all of them is matching against golden list or white list, then you can make sure, okay, this system is capable what you are requiring. And you can trust in the system. You can release some secrets on the remote machine and start to process your confidential data. And this attestation report will be consist of two parts: the platform attestation token and the RAM attestation token. We will talk about these details a bit later. And I have put a link here, the CCA confidential compute architecture security model, which contains some more high-level requirements about these flows. And later this year, there will be published on RMM. This is the RAM management monitor layer, RMM spec, which will contain some more details, token and token flows. If you are not familiar with this confidential compute architecture, that's just a few words about it. That next to the normal and the secure world, a new word, a realm word, will be introduced. And in this realm, it's very similar to how virtual machines is started. A realm is basically a virtual machine. So you can dynamically start VMs, and those VMs are hardware isolated. The memory area of those VMs are hardware isolated from each other and from the rest of the world. So even the secure world has no permission to look into certain RAM memory. Okay, next slide. Measured boot. What is measured boot? So we need to distinguish trusted boot and measured boot. Trusted boot means that you have the boot flow, all the images are signed, or you have a certificate chain which corresponds to certain images, and it starts from a immutable bootloader, which usually lives in a read-only memory, and in each step the bootloaders are validating the signature and the authenticity of the next image, and if that is correct, only load those images. Measured boot is a bit different, but can be part of the trusted boot. Measured boot means that you want to know later in time, when you are in runtime, that what firmware components and other data was loaded during the boot process. So your bootloaders measuring the images, which means that computing its hash values, and record somewhere these values and make it later obtainable by high-level software. So you want more precise information than software version. I have software version XYZ running here. That's not enough. I want to know for sure which exact binary was loaded on a certain system. That's why the hash value is computed and recorded. Last year or a year before in TFA, the measured boot was added as a feature. It works like that the bootloaders do the measurements. There is a shared buffer where these measurements are recorded. There is a certain data format. This is defined by the trusted computing group. This is used in the TPM event log format. All the measurements are put in this shared buffer. The address of the shared buffer is passed around the boot flow. So later, bootloader images are inheriting the address of the shared buffer from the previous bootloader. And at the end, when the secure word is booted, some secure service or trusted application gets the address of this shared buffer and can answer TPM request or whatever. Also, the non-secure word get copy about this buffer, so the Linux also can access this data or extend with more measurements during its boot time. With CCA, Confidential Compute Architecture, a new way will be introduced. How can a system record this measured boot data? The CCA security model strongly recommends to have a secure enclave next to your AP core. So you will have an AP core, and you will have a secure enclave, which memory is isolated from the AP, but there is a communication channel between the two. And this secure enclave can provide security services to the AP core to ensure its required security properties. And one of the services which is provided by RSS will be the measured boot. So AP can request RSS to please store me these measurements, and later those measurements can be read back. The two-way, the event log-based measured boot and the RSS-based measured boot can coexist in the future, and platform owner can decide which one to use. Okay, the next slide is about a bit more details about the flow of attestation and measured boot. But first sentence, how measured boot and attestation are related. So I mentioned that in the attestation report, you will get information about your system. One of the most important information that what software components are running on the system. And that's when measured boot comes to the picture. So during boot time, you use measured boot to compute those measurements and record them. And when you are requesting an attestation report, then you are obtaining those measurements, including in the attestation report and sending back to the requester. What are the responsibilities of the components in the system regarding attestation and measured boot? On the right-hand side, there is the RSS. This is the secure enclave. It implements the functional requirements and the hardware isolation requirements, which is described in the CCA security model. So it's a hardware component which has firmware which fulfills certain requirements coming from the security model. This is the boot of the trust. This boots first when the device gets power. AP and other cores which might in the system, they still kept in reset. RSS authenticates its own images and after authenticates the initial images of the other cores. So RSS will authenticate the initial image of the AP and might other cores, for example, SCP. Then it will pass on the execute. Then it will release the other cores from reset and they can boot as usual. Later, during runtime, RSS provides certain runtime services to the other cores. One of these services is measured boot and the other service will be attestation. And there will be others, but it's not in the scope of this presentation. On the left-hand side, you can see the AP core, and in the AP side, a new exception level, the RAM EL2 appears. In the RAM EL2, RAM management software we are running. That is which is responsible to load the RAMs in collaboration with a non-secure host, and its responsibility to provide the attestation report on the request when an in-RAM software requesting an attestation report. In-RAM software also can do measurements during its boot time. UEFI support measured boot. Kernel has a module which can record the measurements of loaded binaries, and in all these measurements can be recorded by RMM. It provides an interface to the in-RAM software to record measurements, and also provide an interface to request the attestation report. When requesting the attestation report, the RAM management software will be responsible to collect all the piece of information which need to be put in the attestation report, create it, sign it, and send it back to the in-RAM software. Next slide, a bit more details about this data flow, what I have previously described. The best if we start on the right bottom corner and we are following the usual boot flow of the system. So if you are checking the box, the CCA has responsibilities. You can see in that box, these are the major components which need to be present in order to support attestation. We need the service, the measured boot. We need an attestation service, some crypto to sign the attestation report. We need to access to signing keys, which are pre-provisioned to the chip. Need to read device lifecycle, hardware ID, and other properties of the system. It boots first, authenticates the images, and record the measurement of its own images. Later provide service to request measurement store request from other components, SCP and AP. it has an own attestation key. This is called the initial attestation key, and it creates one report. This is called the CCA platform report. So I mentioned on the first slide that the final report will consist of two parts: the platform attestation report and the realm attestation report. The CCA HES or RSS is responsible to create the CCA platform attestation report. It contains the measurements, all the software components, which has the capability to ensure the system security of properties of the system. So anything which is belongs to the trusted compute base of the in-RAM software, all those measurements are part of the CCA platform attestation, and also hardware ID and so on. And it also creates a subsidiary key, the RAM attestation key, which will be used later by the RAM management software to sign the other halves of the token, the RAM attestation token. At boot time, RMM and RSS has a communication to exchange data, the platform attestation token, and this RAM attestation key will be requested by RMM from RSS and provided. The platform attestation token is created at boot time. It's constant. It doesn't change in the lifetime of that power cycle. It change only if you do a firmware update or open up an external debug session, which has an impact on the device lifecycle. But those operations can be done without a system reset. So if you want to do firmware update or external debug, you anyway need to reset your system. And after the reset, these modifications will be reflected in the platform attestation token. The RMM, when get this information, the platform token and the RAM attestation key, they will cache these info in the power cycle. It will accept measurement store request from the in-RAM software, and on request create the RAM attestation token. The RAM attestation token will contain information about the in-RAM software. What's the measurements, which was recorded, some ID, and so on. And these will be signed with the RAM attestation key. At the end, the two parts of the token will be concatenated, so single report will be formed from the two halves, and that single report will be retried by the remote verifier. The format of this token is standardized. It has a CBOR encoding, and there are cozy signature around that. More details will become in the RMM spec later this year. Yeah, I guess that's all. We can jump to the next slide. Here's a bit more detail about the token. There is a figure which helps you to visualize how well it looks like. As you can see on the bottom, there is the CCA platform attestation token, which is created by the RSS, and at the top there is the RAM token, which is created by the RMM, and the two token is forming single attestation token, attestation report, which send back to the requester. Requester can send in a request a challenge value. That challenge value is meant to ensure the freshness of the token to avoid replay attacks. The challenge is included in the token. Between the two halves of the token, there is a cryptographic binding, so they are valid only together, and you can validate whether they belongs to each other. and not might maliciously just formed. This is achieved that the RAM attestation key, public key, is included, its hash is included in the platform attestation token. RMM at boot time will query the RAM attestation key and the platform attestation token and cache them in the power cycle. Okay. I mentioned that to exchange these data, we need some communication channel between the application core and RSS. So here is a few points about what was our design considerations when we created this design of this communication. Actually, the patches which was sent to Requio this week are limited to this AP and RSS communication. So only boot time will be some communication between AP and RSS from CCA has point of view. Later, might implementer can add other communication channels or reasons why to communicate with RSS, but from CCA has point of view, only at boot time is message exchange. At runtime, basically there is almost nothing. So we have created a simple MAU driver. There will be an MAU link between all the exception levels in the AP core and the RSS. This MAU driver is part of the BL1, BL2 images. Those will do the measurements and also the runtime BL31 image, because through that image can RMM request the platform attestation token and the RAM attestation key. During the boot, we have only one core is alive. The rest of the cores are kept in reset. So the communication channel won't be prepared for concurrent calls. The calls have a blocking semantics, so AP need to wait.
Sorry, question. When you say it's not prepared to handle, you mean it'll error out, right? As opposed to allow bad behavior.
It's not prepared to handle right now.
Okay, so basically if there are concurrent calls, you can do bad things.
Yes. Yeah.
Okay, all right. Yeah.
Yeah.
Okay, I suppose it will get fixed eventually.
Well, the design so the design that we envision doesn't require to have multiple cores run at that time. But of course, if there is a scenario, then we can add support for concurrent calls. But
I'm not asking for adding support for concurrent calls. I'm saying you must explicitly error out if there are concurrent calls, right? As opposed to allowing undefined behavior. So
yeah, okay,
that's why it wasn't clear what you meant by calls not handled. You probably means are not allowed.
Yeah. That is the intention. Yeah. Okay. The cores have a blocking semantics, so the AP core need to wait until the answer from the RSS is received. If there is any error during the measured boot and attestation at the beginning, they are handled as fatal errors. So there is no point to boot in really, because your attestation request later will be failed anyway. So if this is a confidential compute architecture and your attestation it fails, then there is no point to start a RAM on it. Between ES3 and RSS, there will be only a single MAU channel. So we keep the proposed API very simple. So there is a buffer and the size, what data we want to send, and there is another buffer and size information, what data is received from the RSS. Always the AP initiate the communication, AP request and RSS response. The protocol layer looks like that we borrowed from the TFM. So as you might know, there is a TFM project which is aiming at M-class devices and creating a standard framework how to invoke secure services from the non-secure side. And RSS software will be based on TFM. So we are borrowed the APIs and the protocol layers from the TFM implementation. And the usual PSA APIs are abstracted, and those are called from the rest of the AP software, like Measured Boot. The interfaces are not meant to be generic interfaces, so they won't be available from the secure, non-secure world. They are restricted only usage for the ES3 software.
So sorry, quick question on that. All those APIs are overridable by a platform and adaptable to whatever implementation they have. Not everyone may use FFAM or MHU or whatever else, right?
If that platform implements the PSA APIs, the underlying part, what is the communication channel protocol, then that can be replaceable.
Okay, so the platform implements the PSA APIs, and that's at a higher level than this communication protocol.
Yeah. So the generic code is relies on the PSA APIs.
Okay, all right.
Again, the last slide about the measured boot in RSS. How will it behave? It is an alternative backend next to the event log solution. Event log solution is fully provided by the AP core with this shared RAM buffer solution. RSS provides more security due to its hardware isolation. It's more like the TPM way of doing things when you have a distinct chip on the motherboard. That's a TPM chip, and the system can send over I2² line measurements to store them. In this case, the secure enclave probably won't be a distinct IC on the motherboard. Instead, probably will be in the same die as the AP, but there will be hardware isolation around. From AP core, it's configurable that which software component measurements or which software components should be stored in RSS and what should be stored in the event log. So that's the platform implementer decides. At this point, only the VMware TCB, which only those software components which belongs to the VMware TCB will be stored in RSS. So for example, the secure world software is not part of the VMware TCB because they are isolated. Secure world cannot touch VMware, but for example, monitor world can. So the secure world software components won't be stored in RSS. Might be later, platform implementer can decide that secure and non-secure can also access to RSS. And of course, within RSS, there can be also some isolated software environments. The measurements will be stored in the RSS internal SRAM, so there is no special hardware in board like TPM or PCR registers. They will be stored in internal SRAM, the so-called measurement slots, but it's just RAM. How many slot is supported by a certain implementation is implementation defined. The measurements will be stored in the extend fashion. That means that you can store multiple measurements in the same measurement slot. And it means that the old value of the measurement slot is concatenated with the new value which was received. The hash will be calculated, and this hash value is written back to the measurement slot. Yeah, and not only the measurements values, I mean the hash values will be stored, that metadata can be stored alongside. What kind of?
Yeah. Is there an option only for one algorithm to be used for calculating hash value, or can we have multiple algorithms?
It's configurable.
It's configurable, but only one at a time.
Yes, I think in the current team, I mean, there is one algorithm on the AP side, but what to use to measure software components.
Okay.
And when you send that measurements to the secure enclave, there is another algorithm what to use when you do the extend operation.
Right.
Yeah. So in this sense, there is two different hash algorithm, but on software components level that you want to measure these set of software components with SHA-256, but there is another group what you want to measure with SHA-512. That is not supported currently.
Okay. Okay. But then there is no restrictions on, you can use anything like SHA-512, SHA-384. It's user defined, right?
Yeah, it's user defined.
Yeah. Okay. Thanks.
Yeah, and there will be metadata along these measurements. For example, hash algorithm identifier. You can store some small strings like software version 2.6 something. This can help the report verifier to look up what's running on the system. And the mandatory metadata is the signer ID. The signer ID identifies that which authority has signed that certain image. This basically is the hash of the public key, which can be used to authenticate the image.
But I think the larger implication of Mayur's comment is that it will be good to have algorithm agility like the TPM has, and other attestation protocols like SPDM, right? So that gives the verifier a chance to choose what their security policy is and what what crypto algorithms are used, right? I'm not saying it needs to be done immediately, but that's something you should definitely keep in mind while designing these APIs.
Do you mean that when requesting the attestation report, you should request certain algorithm to use for the measurements, or?
Correct. Yeah.
Okay.
The verifier can say, hey, yeah, your platform can support SHA-256, SHA-2, SHA-3, whatever, right? And depending on what your security policy is, and depending on the situation, you might want to use different algorithms. So it might be worth considering, allowing the verifier to select from a list of supported algorithms.
Yeah, if I go back to this figure, so I know that in ES3 and in RSS, these configurations are only supported at build time, but probably in the RMM domain, when you are launching RAM, that could be configured at RAM launch time, what algorithm to use to measure. So that's the current situation.
Okay, understood. Yeah, it will be useful to extend that, I think, going into the future, to have that kind of agility to extend it all the way to your root of trust for measurement.
Yeah. Okay. Thanks for the feedback.
I can ask one brief question, Tamas. It's about, in one of the slides you did mention that Realm attestation token does include nonce for freshness. That's good. But how about, for example, if Realm, for example, wants some user data, maybe digest of user data to be included in attestation token? Like that's very typical use case, for example, when it comes to secure enclaves and how they use attestation. Is it possible?
Yeah, you mean that in-RAM software has a certain data which
Yes.
he wants to somehow bind to the attestation token.
Yes, exactly.
Yeah,
For example, I do generate on the fly the ECDH key pair. I want to include digest of my ECDH public key in that attestation token and send the token as well as attestation token, and that might public key to a verifier or relying party. Then they can actually establish trust to that. That's the basic specific use case.
Yeah. So it can be achieved in a way that you are received the nonce from the requester. You are creating a data blob from the nonce and your public key, calculating its hash value. That hash value will be the challenge in this figure. So that will be part of the attestation token. And you send your attestation token and the previously created data blob, which has the original nonce and the public key, sent back to the verifier. In this way, the verifier has the capability to check these bindings, the links between the certain blobs, and build up trust towards that key.
All right, thank you. And one more question. This is also related to the use of algorithms. I think when it comes to what kind of signature algorithm that we want to use, it's pretty much up to the CBOR object signing and encryption, right? I mean, since you are using that kind of encoding, CBOR encoding, that's basic. I mean, it can be anything. Like you are not requiring some specific algorithms, I assume.
In the CCA security model, there is a section about recommended crypto algorithms, but it's just a recommendation. So the implementer, I can guess, can defer if he has a good reason and it's secure. The current library that we are using supports elliptic curve signatures.
Right. So basically,
Yeah,
as far as I can see, ECDSA curve P384 is the one recommended.
Yes.
Okay.
And in the reference implementation, that curve will be used.
Is it easily changeable? Is it configurable? Or hopefully it is, right? So let's say I want to use a different curve. Is it just a matter of changing a few defines?
Yeah. At build time is easily configurable.
Okay.
Yeah, but it's also, so it's depends on the capability of the library, what is used by the implementer. For example, RSA algorithm also might used, but if that certain library doesn't support RSA signatures as a COSI signatures, then yeah, it's a big work to add that support. So that's why I highlighted that certain library that we are using supports the ECDSA curves.
Okay, thank you. One other question, right? Maybe this is my lack of knowledge of the CCA architecture is when is the realm, the realm page is measured? Is it when it is created, or as the realm starts running? I suppose it's before, right? Before it starts running.
We are talking about two different types of measurements. So there is a RAM initial content measurements. What is measured when the RAM is created. So your host, non-secure host, is start to populating the data to the to your freshly created RAM. Probably that will be a very basic content bootloader, for example, UEFI bootloader. And before that RAM is activated, the data of those memory pages are measured. This is the RAM initial content measurement, and it is recorded and part of the attestation token. And later on, when you have started your RAM and the UEFI started to executing, UEFI also can load, for example, the kernel and can measure the kernel. And the kernel also can measure certain user space software which was loaded. And RMM provides an runtime interface to record these measurements, which is also stored in an extendable fashion. These measurements are called the realm extendable measurements. So you have two set of measurements: the realm initial content, which is only single measurements, and there are the realm extendable measurements, which comes from the in-realm software at runtime.
Okay, that's very interesting.
Yeah, does it answer your question?
Yes, that does answer my question. Thanks.
Any more question?
A small curiosity question. Can you elaborate a bit on the choice of FFM or TFM for the as protocol? Why I justify this choice?
You mean between RSS and AP? Yeah, basically it was chosen because RSS software is based on TFM. So it was a natural choice to use a protocol which is supported by that software already.
Mm. Okay.
Okay, if there is no more question, then thank you all for attention.
So perhaps if you stop sharing, I can show folks if they're not aware of the mailing list and the Gerrit patches that you've upstreamed. Let me share my screen. I can find the right screen. I think it's the desktop one. Hopefully you can see my screen, can you?
Yes.
Yeah. Okay. So this session has been held on the back of some an email to the mailing list Tamas has issued, I think, on Monday. So if folks aren't aware where to look, I'm sure most of you are, but if you look at the mailing list link from the TFA page, you will find that there's the archive, and it is just for reference. I'm not sure when people will be watching this video, but this is April 2022. In the archives, you will find there's a CCA attestation and measure good post that Tamas did on Monday that gives some description, and this session is a little bit more in depth to what was provided here. But also, as you can see, there's a link here on the actual patches that have been upstreamed for TFA, for the TFA aspects of support for the solution that Tamas has been indicating. So you've got a number of patches here that are available for review if anybody wants to do that. I'm sure Tamas would welcome any follow-up comments to his email thread if you need to follow up after this session. But yeah, I just wanted to point them out in the recording in case folks want to follow up on these things.
Yeah, thanks, Joanna.
If there's nothing else, we can finish 15 minutes early, but hopefully today's session was of some interest to folks.
Yeah, very useful. Thanks again for setting this up.
All right, everyone, welcome.
You're welcome.
Hopefully we'll have another session in a couple of weeks if we've got a topic. And I will say at this point, if anybody, any of the community have got a topic they would like to share with the rest of the community, please reach out to me. I'm happy to, I'm always looking for subjects to talk about. But if there's nothing else, I'll see everybody at the next session.
Thank you.
Thank you.
Thanks,
Bye, everyone.
bye.
Thanks, bye.
Thank you.